Hello. In our last video, what we did was we filled in this table of values. And on the surface, it's simply saying if we have the value of x of -3, -2, -1, 0, 1, 2, and 3, and we have x squared plus 2, x squared minus 5, 1/2 x squared minus 1, what would be the output if we put -3 into it, -2 into it, and so on and so forth? Well, we know what we're studying here are quadratic relationships or quadratic functions. And our endpoint is to be able to graph these very quickly using a couple rules that we develop. And these rules are actually very important when we look at other types of relationships as well. However, we start with just simply the quadratic relationship. So the next question is, well, how do we graph these? So what we do is we imagine really when we have x squared as y equals x squared, y equals x squared plus 2, y equals x squared minus 5, y equals 1/2 x squared minus 1. So if we come down here, we want to go through and graph these. So again, when you're graphing these, what I do recommend is have some colored pencils. If you're not working on a computer, which is probably more the norm nowadays, still, colored pens are great, but if you have a computer, you have all these colored options. So I like to underline each one I graph. So we're going to start by graphing y equals x squared. And remember, we're interested in a quadratic relationship. This is called the parent function, parent relationship, parent graph. The idea is this is what we start from. We want to be able to close our eyes and envision what y equals x squared looks like. And as opposed to filling in a table of values to do each of these, what we are heading towards is this idea of applying these transformations. So if we have y equals x squared, we know we have the point 0, 0, 1, 1, 2, 4, 3, 9, -1, 1, -2, 4, -3, 9. And again, then I connect these with a nice smooth curve. I'm going to try and make this kind of like a U. Be very careful. Don't make it a V. If it looks like a V, it's wrong. It's actually a different type of relationship then. Don't forget your arrows on the ends. Okay, and again, when we look at this, we want to be able to say to ourselves right away, the vertex is 0, 0. The axis of symmetry is x equals 0. Remember, an axis of symmetry is an equation which represents the line that this graph is symmetrical about. So we know that this graph is symmetrical along the line x equals 0. And we want the direction of opening. And the direction of opening is upwards. So now what we're going to do is we're going to do each of these other graphs. So let's do y equals x squared plus 2. Now of course, what I could do here if I didn't know what to do is I could come up here to this table of values and simply plot these points. So if x is -3, y is 11. If x is -2, y is 6. If x is -1, y is 3, and we can continue along, of course. But what we want to start doing is understanding this idea of transformations. So what we see here is that I'm adding 2 after I apply the parent operation. And the parent operation here is the squared. So what it means is that from my parent graph, which is y equals x squared, I'm taking whatever the y value is here, and I'm adding 2 to it. So if I go to my parent graph, which is this green graph here, all I do is I have to take each point and just go up 2, 1, 2, up 2, 1, 2, up 2, 1, 2, up 2, 1, 2, and then up 2, 1, 2, 1, 2, and there is my graph of y equals x squared plus 2. So what I've done is, as opposed to doing this labor-intensive table of values, I see that I just take my parent graph and shift it up 2. And of course, I look at this, and even if I'm not asked, I want to ask myself, well, what is the vertex? The vertex is, of course, where we change direction, so that is going to be 0, 2, being sure I have to give the coordinate pair. Then I want to ask myself the axis of symmetry, And notice the axis of symmetry hasn't changed, so it's still x equals 0. And I want to do the direction of opening, and the direction of opening is up. Remember, in our previous lesson, we learned the only thing that changes this direction of opening is if this a value has a negative, is negative. So there's a negative in front of there. So all of these graphs I can see very quickly are going to open up. Let's do the next one. Y equals x squared minus 5. So again, if I take my parent graph, which is the green, I see that I'm going to take all my y values and go down 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now what you might notice here is that this graph doesn't actually change shape. Notice this blue graph has the exact same shape as the green one. And the gray one, which is y equals x squared plus 5, is going to have the same shape. So what some people sometimes do is they just translate the vertex just now to there, and then they just literally graph out their parent graph. So over 1 up 1, so over 1 up 1, over 1 up 4, sorry, over 2 up 4, over 1, 2 up 4. It's going to take me to there. Over 1 up 1, over 2 up 4, over 3 up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, over 3 up 9. I can just come across, I can read that. And now I've transposed all the different points on my parent graph. But this graph might actually have another point on here. So if I'm dealing with y equals x squared minus 5, I can get most of the points by looking at my parent graph. But what is nice to do sometimes is just to test some values. So let's test x equals 4. So that means y is going to equal 4 squared minus 5. That's 16 minus 5, which gives me 11. So now I know 1, 2, 3, 4, 11. So I have to get that point there. And of course it's symmetrical. So if I'm at 4, 11, negative 4, 11 is a point as well. Now I get a nice smooth curve. And there's my resulting graph. So this last one is a little bit different in that it has an a term in front. So let's do this one using the table of values. So we see we have 0, negative 1, 1, negative a half, 2, 1, 3, 3.5, 2, 1, 1, 2, 3, 3.5, which is somewhere right there. And now remember this is symmetrical, so it's going to have the point there. If I go 1, 2 to the axis symmetry, 1, 2, 1, 2, 3, 1, 2, 3. So let's actually come down here. Y equals 1 half x squared minus 1. So let's test x equals 4. So I'm going to have y equals 1 half times 4 squared minus 1. 16 over 2 is 8. 8 minus 1 is 7. So we're going to have 4, 7. And now let's test 5 as well. So we're going to get 1 over 2 times 5 squared minus, 5 squared minus 1. So that's 25 over 2, which is 12.5, minus 1 is 11.5. So it's just off the graph. So that means, again, I can use a symmetrical argument and come to the center over, that should be on there actually. There's that one. And the last one's going to be at 5. It's going to be just above. Just above. And there we go. And of course, I want to remind myself, the vertex, always checking this. We see 0, -1. The axis of symmetry is x equals 0, and the direction of opening, is up. Let's do the gray graph as well. The vertex is going to be 0, -5. The axis of symmetry is going to be x equals 0, and the direction of opening is going to be up. And there we go. So again, just to sum up, these are all different relationships which I could graph with the table of values. But what we're heading towards is a method to graph these where we think of the parent relationship or parent graph or parent function, it's all the same thing, and then applies a set of rules based on the position of specific values in the relationship. I said the term briefly in this parent operation. X squared is my parent operation. It is the operation which dictates what the shape of the graph is going to look like. And what I'm going to suggest you do now is, after you finish this, take a look at all the information for each of these relationships. And what I mean by that is the vertex, the axis of symmetry, and the direction of opening, and look at the relationships and see if you can find some interesting patterns there so that you can pull out this information without actually graphing. I hope this video helped.